Hello everyone, welcome to this tutorial on clustering and also text feature extraction with me. Um, I record this tutorial as a midterm exam preparation for Intro to AI and Data Science course in Fasilkom UI. Let's just start. The first task you are going to uh, explore is about these text similarities. So suppose that you have three documents which contain the tokens below. You can see it on your screen. We have this D1. I'm sorry, let me just using the pen. We have D1 over here, and then we got D2 and as well as D3. We also have one query which contains these words over here, these tokens. So this question asks you to use this TF-IDF representation to determine which document is actually the most similar to the query. And for the distance matrix or the similarity matrix, we can use this cosine similarity. And I will explain to you later about why do we use this cosine instead of other similarity measures. And because I have already preprocessed these tokens, then you don't have to do the preprocessing activities for this question. So let's just start. The first one is you want to generate this term document matrix, or perhaps people say document term matrix, because you can see why does it is called document term matrix. It's basically because this is the document and this is the term, right? So this kind of table will be used later to generate the TF-IDF, and we will see the relation between this table and the TF-IDF table later. Um, you have to understand that since query and the document must be in the same vector space, because we cannot compare the vectors if they are located in a different vector. It's like compared, if you have learned about linear algebra, you can compare this vector in polynomial space with another vector in matrix space. That doesn't make any sense, right? So we have to include the query as well in the matrix. And this is actually the count factorizer. If you use this library provided by sklearn, the count factorizer actually generates this kind of matrix. And how to interpret this matrix actually? So we can see this one. So basically, if we take a look at this cell, then this cell actually means that there is one occurrence of that word in document 3. So that's pretty simple. And that's how you interpret this term document matrix. The next one is we are going to talk about the TF-IDF. So this is pretty heavily, this kind of like need heavy computation, but we will walk through it together. So basically, you have to fill this TF-IDF uh, columns over here to get the vector representation, right? So you have to remind again about what is actually DF and IDF. IDF stands for inverse of document frequency. So in order for you to know IDF, then you have to know about the DF itself. So what is actually DF? DF is document frequency. Uh, it states the occurrence of certain term in the corpus. Like for example, if we take a look at this 2 over here, then the df of she is 2 because there are two occurrences of she in the corpus in D1 and D2. If we take a look closely, in the D1 and D2, we got this she, right? So we have to write 2 inside it. And how about really? We can see that really got 4 occurrences in D1. Do we include that? Apparently no. So basically, um, you only count you don't consider the number of occurrences of that word in certain sentence. It is kind of like boolean, right? It is only 1 or 0. So if it exists in certain documents, then you will consider that as 1. and otherwise we will consider that as zero. So there are only three occurrences. Um, Maybe I should restate my word. It is not three occurrences, but um, I would say that there are, yeah, perhaps it is quite good to say that also, because there are three actually occurrences of really in the corpus, but in a unique way, like SQL using distinct. So um, we only basically, in order for you to determine the DF, you can all basically count how many cells in this specific column um, which are not zero. And in this case, we got three. So the document frequency of really is three. Yeah, that's it. And the same as well for the rest of the terms, actually. And how to compute the IDF, the inverse of document frequency. So the inverse is just basically you can um, doing this log and over df of that word. So it is log and over df. What is n? N actually is the number of documents in the corpus. So because we have four documents including query, then we will say that this is four, and the df of she is 2. So log 2 is equal to it is equal to 0.3. So we will put this 0.3. We have already got this IDF for all terms, right? For this column. The next one is we are going to compute the TF IDF. So basically only the TF takes um, the occurrences of each word in a document into account. So we don't consider that in DF, right? Like I've told you before. So the TF is basically um, the number of occurrence of certain word in the certain document. Like for example, if we take a look at this one, TF of D1 and she is equal to 1 because there's only one occurrence of she in D1. How about really? We got 4, then so we have to put this 4. And how to compute the TF IDF? We can just multiply it. So we got the IDF is 0.3 over here, and we got the TF is equal to 1. So we can just multiply, and we got a 0.3. And the same as well for this one. Can just compute and we can just multiply between this one and this one. We got this one. Well, actually, this is not um, the exact two decimal places. So this includes kind of like rounding. So you can see that it is not exact 0.48. And the same as well, you can do this the same techniques to compute the TF-IDF for D2, D3, and query. So basically, I've said before that there is this kind of like correlation, or I would say um, this this table is actually a subset of this table. Why? Because if you can see this TF, it is basically the factor that you saw earlier in this one, right? But in the transposed version, because you can see that the factor over here is actually a row factor. Meanwhile, this one is actually the column factor, right? So that's how you compute this TF IDF. So where is the resulting TF IDF factor actually? Well, the resulting factor is actually the TF IDF column for every document. So the resulting matrix will be like this. And this is actually what the TF IDF factorizer, if you use this in sklearn, would generate for the document. It's pretty straightforward. So the next one is we want to compute the similarity using cosine similarity, like I've told you before. And just to give you a brief introduction, it is actually a better option when it comes to text processing compared to L2 distance or Euclidean distance, because this cosine similarity takes the angles into account. Not it is not basically distance based. So um, yeah, for a more clear example, I will explain later. So suppose that we have these two documents over here. I'm sorry, D1 and D2. So D1 consists of 11 tokens, and D2 consists of 2 tokens. Then we want to visualize it in the vector space, the artificial and intelligence vector space. So it is basically look like this. So this is the D2 and this is D1. Then if we want to compute the similarity using the L2 norm, the result is this one, right? Would be a very large number. So using the L2 norm will kind of like make these two factors kind of a very dissimilar because the norm is very high. But in with our common sense, we can understand that these two factors are actually similar. Like since we all know that basically D2 is kind of like subsets of a D1, so it is not that dissimilar. Then what if we use the cosine similarity, which actually computes angle between factors? So this is what we focus on when computing this cosine similarity. So uh, it got affected by this kind of like um, I would say the term of I'm sorry, the occurrences of the term, but not so much. It is much a better option compared to L2 norm. This is the formula for the cosine similarity. So basically, it is pretty simple. This is the dot product over the norm of A, the first factor, and the norm of the second factor. And in order to um, delve deep into this um, properties of this cosine similarity, you have to remember again the basic properties of cosine function. So the cosine functions actually, oh, I'm sorry, this is not zero actually, this is -1. I will revise it later. So it it actually it is actually ranging from -1 to 1, and if we take the absolute value of this, we could get this cos okay 0, this one, right? And you have to remember that this cos 0 is equal to 1, cos 90 is equal to 0. So uh, the higher the cos theta the higher the cos theta value, then the smaller the angle between these two factors. Because if there is no angle, I mean, like if it's kind of like this one, then it is actually equal to 1, which means very similar. And indeed, it is very similar because these two are basically the same factors. And the lower the cos theta value would indicate that the two factors are more dissimilar. So that's actually the basic of cosine. Let's just apply this one. So in order to compute this D1, the norm of D1 is basically you can use this, uh, yeah, this is kind of like Pythagorean theorem, but generalized Pythagorean theorem. You can compute this one, 0.3 power to 2, 0.5 power to 2. You can sum it all and take the square root out of them. The same as well for this query, and you can compute the dot product by multiplying this one and this one, and then you add with this one and this one, and so on until we get this one. We got 0.03. To compute the cosine similarity, we can just divide this 0.03 by 0.61 times 0.35, and we got the score is 0.15. So the similarity between uh, document 1 and query is 0.15. Well, using the same method, we can just compute for the rest of query document pairs. We can get 0.15, 0, and 0.38. If you take a look closely between um, these D2 and Q, why the value is 0, it is basically because D2 and query, this is query, right? It's not the same, right? Not, it's not the same as well. Really, they don't have really like in this query. And like, we got one um, intersection between these two, math, and it is different with this artificial intelligence. But since like also appears in every document, then the TF-IDF would consider that as 0, so it doesn't have any meaning. And thus you can see the result is 0. So the most similar document query is actually D3, and it is actually makes sense if you take a look at this, because D3 is actually the superset of Q. Not bad result though. Let's just continue. The next one is we are going to do clustering, but before that you have to reduce the dimensionality of this representation, since we got these 10-dimensional factors and it would take a long time to compute the clustering result. So I will just reduce dimensionality so that it consists of 2 features only. There are so many ways you can review it and again, and I will use this one. Perhaps you haven't heard about it before. So basically, LSA is basically um, one of like the most powerful non-neural network algorithms for topic modeling task in natural language processing. But since it is quite complex actually, I will not explain about that in detail. So let's just apply this one and assume that the result is this one. This is what we call the latent factor 1, and this is the latent factor 2. So the next one is we are going to apply apply the clustering using the k-means. You have to remember the steps again. You have to choose the k initial centroids randomly, and for each point you have to assign the point to the nearest centroid, and then you can recalculate centroid positions using mean. So this is basically why it is called k-means, and you can repeat that until the convergence has been reached. And for this question, you are asked to do this basically with 2 clusters and Euclidean distance. And for the initial centroids, we got this and this. And you have to do the iteration 2 times. So this is the visualization, basically, and this is the initial centroids that we have defined before. Okay, so you can create a table like this in order to ease yourself to like ease the computation, I guess, because I used to use this kind of like table as well in the past when I was working on this k-means clustering. Anyway, let's just start the iteration. So this is the first iteration. So we got the points, 4 points over here, and we got this centroid A and centroid B over here. And this is the cluster assignment. How to populate this table? Well, actually, we can just use the Euclidean distance as stated in the instruction. So you can use this one, and you can just take the difference and take the power of 2, and you can sum it up with this one and take the square root of them. You can get this 0.449, and the same as well for this one and the entire table. Then how to decide the cluster actually? So In this case, why do we choose B? Because the distance value from this point to B is smaller than the distance value from this point to A, basically, because 0.449 is smaller than 0.527. And the same applies for the rest of the table. So we pick this B, we pick this A, and A as well. The next one is we have to recalculate the centroid using means. In order to recalculate that one, you can just use simply use the normal means for the data. I'll say equal I from 1 equals until n. We can just for example, the data um, is put in this variable called data, and this one is just basically can index it, and oh yeah, this one there's no need actually. I'll just put this one and times 1 over n, the basic means calculation. So for this one, the centroid of A, how to determine it? We got this A, 2 points clustered um, to A clusters, and to compute the new centroid is just basically you can mean this one, take the mean of this one, and take the mean of this one. This one is for x, this one is for y-axis. You can see this here. You can get 0.419, and this one you can get minus 0.329, and the same applies for this centroid of B as well. After you update the centroid, you can just repeat the iteration using the updated centroid, as you can see, and you can use the normal Euclidean distance to compute this one. And we can see that the cluster assignment using uh, the same method like the previous one. So um, let's just move on to another example. So this is basically another example. um, I collect this example from last year's regular class slide. So suppose that we have these 8 points over here, and the initial clusters is actually this one. 2 point. I'm sorry, it's not point. It's supposed to be comma. 2 comma 10, 2 comma 10, and then 5 comma 8 and 1 comma 2. You are asked to use using this rectilinear distance. So this is the initial centroids over here. In order to populate this table, you can do the same steps by using this rectilinear distance, computing between this one, and between this one, and between this one. And you can see that because this one is the smaller number compared to these two, then you can assign this point to cluster 1. Okay, the same as well for the next one, for the rest of the tables. Then we have to recompute the mean again. For cluster 1, since it is only consists of one data over here, we can just take this one, 2.10, get this one. And for cluster 2, because there are five points clustered into the second one, then we have to mean these 5 points. You can just 8 plus 5 plus 7 plus 6 plus 4 divided by 5, because there are 5 points there, and the same for this y-axis value. And for cluster 3, we can do actually the same. Take this one, take the mean of this one. So basically 2 plus 1 divided by 2, and 5 plus 2 divided by 2. It is 1.5 comma 3.5. Okay. we already got the new centroids. Then we have to update the centroids. And then we can just recompute all those distance over here and reassign the cluster. Then you have to recompute again and do the same thing, and so on. So the iteration will still continues until the stopping criteria of the or the convergence has been reached. Then what kind of criteria do I mean actually? So the first one is the maximum number of iterations has been reached. You can see in this link over here, it is basically documentation of sklearn k-means. There is this parameter called max iter. So it is basically to specify the maximum number of iterations. The next one is no or minimum reassignment because we can assure that every problem can get this kind of like pure no reassignments. So no or minimum reassignment of data points to different clusters. And the next one is no change of centroids as well. So that's the stopping criteria for k-means. The next one is, this is quite complex actually, the hierarchical agglomerative clustering. The idea is you have to start with each data point in a separate cluster. So if you have n data points, then there will be n clusters as well. And then you have to merge the closest pairs of clusters until there is only one large cluster remaining. And the history of merging forms a clustering hierarchy called dendrogram. Perhaps you have already um, understood about how to interpret the dendrogram. You have to make sure that you know how to interpret that because it is very important. You have to know how to where to truncate the dendrogram to achieve desired number of clusters. So this is basically the process. So suppose that we have 1, 2, 3, 4, 5, 6. We have 6 data points, and um, therefore we have 6 clusters, 6 initial clusters. For the first iteration, we want to compute the distance between each data points, each data point, and we can get that most the data point with the least distance is actually the same between A and B and D and E. So we can put this here, A and B, D and E. This is basically the similarity for the y-axis, or many people will use this one as Euclidean distance. It depends actually on the matrix that will be used. I'm sorry, the measure. It's not metric actually. And the next one is we already have this 1, 2, 3, and 4 clusters. Then what is the next iteration? Then we want to merge these 4 clusters uh, into the smaller amount of clusters, right? So we can find that these AB clusters, this AB cluster is actually closer to C compared to F compared to DE. Yeah, you have to remember that this is actually one cluster, DE. And um, DE to C is not that close compared to AB to C, and the same as well for DE to F. So we will merge AB cluster and C. So you can see that we can make this um, line over here, and then for the next one we can merge this F to DE. We can create this line over here, and for the last one we can merge this ABC and DEF into one large cluster. So this is the result. So if we want to get 3 clusters, then we should truncate the dendrogram over here. So the clusters that will be made is basically the ABC and the DE cluster, and the last one is F. Mm, Let me see, where is it? 3 clusters. ABC. This one. You got 1 cluster, 2 cluster, and 3 cluster. So that's basically how the how this clustering works. And for DB scan, because this is kind of different compared to k-means and hierarchical clustering, it is basically density based, not distance based. So it can find arbitrarily shaped clusters, and it does not require you to specify amount of clusters. And the last thing is it is kind of like more robust to outliers because this n over here stands for noise. So many people use this method to um, identify if there are any outliers in their data. So that's it. So I guess that's the end of this presentation. So feel free to contact me if you have any further questions regarding what I have explained. Thank you and good luck for your exam.